So we have completed the variable control charts. Now we are moving to the attribute control charts. So for attribute control charts, you should know that we use them when the underlying data is discrete in nature. So what are some of the types of discrete data you may encounter? So for example, if you are measuring the number of non-conforming units, the number of defective units, this will clearly be a discrete data. Or you are measuring the proportion, meaning the fraction of non-conforming units. You take the number of defective units divided by the total number of units you inspect. So this will give you proportion, and this is also considered a type of discrete data. And then we look at the if you look at the total number of defects detected, that is also a type of discrete data. So as we look over here, for example, if you are measuring the number of defective products, an example will be the number of dented cans that's coming out of a canning line. So in this case, you'll be using a number of non-conforming, also known as a NP charts, number non-conforming charts, or also known as NP charts. And this type of charts, they cannot be used if the number of samples that you take at each time point vary. So you must always, if you say n equals to 50, meaning every time I sample 50 cans, you must always be sampling 50 cans all the time. If sometimes you are sampling 50, sometimes sampling 49, sometimes sampling 48, then the n is not fixed, then the next option that you can use is to use the proportion of defective products instead. So in this case, the proportion of dented cans coming out of a canning line. And in this case, you're not plotting the number of dented cans, but just the proportion. The chart that you will be using is the fraction non-conforming, also known as the P chart. So you use them if the n number of each subgroup varies. Then there's also the possibility, instead of counting the number of dented cans, you count the number of dents instead. So in this case, you are measuring the total number of defects. So you count the number of dents in each subgroup, and in this case, you use a C chart. So C basically is the number of number of defects that you count. So this type of charts is less common in the food industry, so I also only briefly touch on it. So there are some fundamental difference between variable control charts and attribute control charts. So as we saw, the variable control charts, they're continuous variables, so you use a normal distribution as the underlying statistics. But for attribute control charts, because they are discrete probability distribution, so you will use either a binomial distribution or a Poisson distribution. So for the binomial distribution, just as a recap that we showed just now, the mean of the binomial distribution is n multiplied by p, so that's why we call it an NP chart, and that's because the center line is NP, and the sigma will be given by this equation. So n is the number of samples in each subgroup, p is the probability of detecting a defect. So we briefly talk about the C chart. So the C chart, you will use the Poisson distribution. So the Poisson distribution is given by these two equations. So the mean is given as lambda, and then the standard deviation of the population is square root of the lambda, where lambda is the average occurrence of an event in a fixed time interval. So in other words, if we talk about the dented cans as an example, so lambda in this case would be the average number of dents you observe, say, in an hour. So these are the equations that we use for the NP charts. So this is the equation for the upper control limit, control limits, and the lower control limits. So N is basically the number of samples in each subgroup, and then P bar, basically this is the average number of defects observed over the entire run. Okay, and then the standard deviation is that of the binomial distribution. So basically what you're seeing, square root NP bracket 1 minus P bar, this is the standard deviation of the binomial distribution. The center line NP, so this is basically the mean number of defective products. So in this case, we talk about the 2 sigma warning limits already, right? So looking at this equation, it is actually quite easy to say what is the 2 sigma warning limit. So if you're talking about the 2 sigma warning limit, you simply change 3 to 2. Then you get the 2 sigma warning limits for both the upper and lower warning limits. So now let's look at an example. So a canned soup manufacturer, they just has established a new canning line, and they want to develop a control chart to monitor the number of defective products. So they collected 30 groups of sample. Each subgroup is 50 cans. So basically N is 50. So now calculate the UCL, LCL, and the center line for a NP chart. So this is the data. So you see that they collected 30 samples, and then each time round they collected 50 samples. And then for the first one, they find that there's 12 non-conforming cans out of the 50. Second one, they detected 15 out of 50 is non-conforming. So these are all the results. So when you plot, you are plotting the number of cans, and to calculate P bar. To calculate P bar, this is the overall probability of detecting a non-conforming can over the entire run. So it's very simple. You sum up all the non-conforming cans. So they sum up for you 3, 4, 7. And then divide by the total number of cans that you have collected, which will be 50 cans multiplied by 30 samples, right? So this is the probability of detecting a non-conforming can for this run. And with that, you can actually calculate the center line. We know the center line is the mean, which is NP for the binomial distribution. So basically, you take 50 times the probability, which we calculated already, 0.2313, you get this number. And then you have the upper control limit and lower control limit. You same thing, you substitute into the equations the right number, and then you can calculate the results, which will be 20.51 and 2.62. So some of the textbook recommend that you round the UCL and LCL to whole numbers. You can do that, or you can choose not to round. It doesn't make a very large difference. The reason why people want to round is that because now you're plotting the actual number of cans that is not conforming, and you are never going to get 20.5 can, right? So their preference is to set the control limit as a round number. So for the purpose of this course, you can round off, you can don't round off, but before you round off, you must show the numbers before you show me the rounded number, okay, for your calculations. So in this case, if you were to round off the upper control limit, you would round to 20. You wouldn't round it to 21, because any point that is touching the upper control limit is still considered valid. It's still considered within control, and any point touching the lower control limit is still within control. So it's only when you exceed. So if you put the upper control limit, if you round it to 21, you're going to have the problem where if you have 21, by right it is out of control already. But if you set it to round it to 21, you would have mistakenly identified it as still within control. Same thing for the lower control limit. You shouldn't be rounding it to 2, because if you round it to 2, it will be too low. You should be rounding it to 3. So if we plot out this chart, then this is what you will get. This is the upper control limit. This dotted line is the 2 sigma warning limits, and you find that these are the points that has exceeded the upper control limits. So this process is out of control. So remember, we also talk about if the number of samples in each subgroup is not constant. So remember, because if it's not constant, then you cannot be using the NP chart. So now we'll be using the P charts instead. P simply means that the center line is the fraction, the proportion of defective products. So it's a P bar. And then this is the equation that we'll be using. It is actually very similar to the NP charts. So let's just go straight into an example, and you'll see how this equation is applied. So let's say you have a company that packs 25 kg bags of rice. So they take one whole container of rice, and then they slowly pack it, or rather they use a machine to pack it into 25 kg bags. So the weight of each bags is then monitored automatically. So the number of bags that did not meet the minimum 25 kg requirement was recorded. So, but they don't produce the same number of bags each time. That's why the N number, the number of sample, is not consistent. Not constant. It varies from 80 to 120. So you see, each time round, the number of bags that they produce is different, and then they are doing 100% sampling. And over here, this is the number of non-conforming units, meaning the number of bags that don't meet the 25 kg limit. So you'll find that it is not possible to find one single N, because the N varies, to substitute into this equation. So that means for each sample, they will have their own individual UCL and LCL. So the first step for this to solve this problem would be to first you calculate the total number of samples. So basically you sum up all the samples, and then you need to calculate the number of defective units. So you sum up all the non-conforming, so you find it's 234. So P bar in this case is simply 234 divided by 2450. You get this probability. And then you can substitute this in, because we know P bar 1 minus P, so we can calculate and substitute in these values. Then for the next step is to calculate the standard deviation for each subgroup. Because remember, this is the equation, we need to calculate this standard deviation. So this is calculated as shown here for, let's say, for the first one. For the first one, you simply take this 0.096 multiplied by 0.904. We have seen how we get this number in the previous slide. Then divide by Ni, with the number of samples in this particular first sample. So it's 100. So with that, you are able to calculate the standard deviation for the first sample. And you can go on to calculate the standard deviation for every sample. So the step 3 is basically to calculate the UCL and LCL, and using again the first one, then the UCL for the first sample is basically you take 0.096, which is the center line, right, plus 3 multiplied by 0.029. So this is the upper control limit, this is the lower control limit. So you should recall that the center line is P bar for this P chart, and we have already calculated that the P bar is 0.096. So then the individual data point that you'll be plotting will be this the sample fraction non-conforming, because remember, you cannot plot the number of non-conforming units because the basis is different, the number of sample is different. So what you do is simply you take this number of non-conforming, divide by the sample size. Then you can get this sample of fraction non-conforming, and you plot these are the points that you'll be plotting. So this is what the final results will look like. You see that the UCL and the LCL, they change, they fluctuate. They are not the same for each data point, and each data point that you see here is the fraction non-conforming. So basically the number of defects, or rather number of defective products, divided by the N for that particular time point. We come to the last control chart that we are covering for this course, and that is the C chart. So C simply means to count the number of defects that comes out of a process. And these are the equations that governs the C charts. So the C chart is based on the Poisson distribution, where C bar is the average number of defects that's monitored at each time point. So if on average your process produces, say, 2 defects per sampling time point, or per hour for example, then C bar will be 2. And then the upper control limit and lower control limit is quite simple, as shown in this equation. So one thing, the key point that you need to know, and you need to be able to differentiate, is to know the difference between defects and defective products. So sometimes some textbook will call them non-conformities and non-conforming items. So when you have a defective product or a non-conforming item, okay, so that item doesn't meet the specification. It means it has at least one defect in it. It can have more than one defect, maybe 2 defects. So as long as one item has one or more defects, it is defective. But the other point is that you can have many defects that's coming out of one process, but maybe they all occur on only one item. So in that case, you have only one defective or one non-conforming item. And the reason why we need to talk about this is that whenever you are counting defects or counting the number of non-conformities, you're using the C chart. Whenever you're monitoring the number of defective or the number of non-conforming items, then you are using NP or P chart. So the key thing is, as long as you are looking at the item level, okay, then it's the NP or P chart that we have covered. If you are counting the actual individual defects can be printing error, can be dents in the packaging. So these are example of defects or non-conformities. So this will then be the C chart. So as you can see, the C chart is not going to be as commonly used in the food industry. So for example here, we have 125 canned foods. They were inspected every hour for defects. So on average, they detect 3.25 defects per hour. So these 3.25 defects, they may occur on one item or two items, but so it's on average 3.25 defects per hour, but you don't know the number of defective items. So nevertheless, the point is we want to calculate the C chart. So if you calculate the LCL and the UCL, so the UCL is basically, the CL is basically 3.25, and then we substitute in the equation, and this is what we'll get, the UCL and the LCL. So I'll leave it for you to try out the equations